There was many changes introduced in the 18th edition, and some of those changes everybody's aware of, but there's some minor little tiny ones there that not every contractor picked up on. So we're going to take a closer look at those regulations and the ones that impact the designs of consumer units. There's a lot of stuff to do with RCD, so we're going to be looking at RCD selection, RCD selectivity, RCD unwanted tripping, Rccb overload requirements. Now, when we talk about Rccbs, they're the RCDs that you would commonly find in a consumer unit. We're going to be looking at integration of devices and components, and then also brushing on surge protection devices. Okay, so Regulation 53133 gives us general requirements for RCDs, and it says that different types of RCDs exist depending on the behaviour in the presence of DC components and frequencies, and the appropriate RCD shall be selected. Now, this puts the onus on you. As a designer, when you're installing a consumer unit, you've got to choose what the best consumer unit is for the application. You're also going to be talking with a client because the budget comes into play. As you know, you can go very cheaply or very expensive with switchgear. So there's a lot of things to be considered, but this regulation puts the onus on you to choose the correct type of RCD. So if you just jot down that regulation, and don't worry if you don't want to take notes, because this presentation will be available on the forum after today. We'll post it up there. Okay, so this one there, it tells us a little bit about the different types of RCD. So the type AC RCD is a general purpose device that detects and responds to AC sine waves only. So you can see the image there on the side of the screen, and you see the little sine wave there. That's a type AC device, okay, and they're the types of devices that we've seen for many years in consumer units, okay. But because now there's a lot more presence of DC in installations, we need to start looking at what types of devices that we install. So next on the list is a type A, okay, and a type A device is used for equipment that incorporates electronic components, okay, and it detects and responds to everything that a type AC device will do, plus pulsating DC components, okay. So it's one better than the type AC. Next up, we have the type F, okay, and this one is equipment with frequency controlled speed drives, and it detects and responds to everything that a type A and a type AC will do, plus these high frequency residual currents. And then next up, we have the type B, and type Bs are often used for electric vehicle charging. It may be PV supplies, depending on what inverter is installed, and these detect and respond to everything that the AC, A and F do, plus they also respond to DC residual currents, okay. So that's the kind of hierarchy of devices. The best one is the type B and the worst one is the type AC. It also goes in price, so the type B will be a lot more expensive than the type AC, so there's a number of considerations there. So looking at this table, this is table 3.4 at the on-site solutions, okay, and what we've given there is the symbols of the devices and some typical loads that you would use on those types of RCDs. So just to recap, that regulation is putting the onus on you guys to choose the correct device for the installation. This is a set of manufacturer's instructions from a Bosch dishwasher that was purchased from Currys in July 2018. Okay, so this is a real life example that these devices are being called upon, and somewhere buried in the back of the manual there's this little description. It doesn't even say that it's a type A is needed, it just gives you the symbol. Use only a residual current operated circuit breaker which features the symbol, and that's a type A symbol. Okay, so it's a real life example that these devices are needed. The issue is you don't know what equipment is in the installation, so you have to be aware that simple things like dishwashers will require a better RCD than the type AC. So just jumping back, what is the problem with a type AC when we have the presence of DC? Well, what DC does is it can blind the RCD. That's how the manufacturers refer to it, as a blinding effect. And what it actually does is the DC can saturate the coil of the RCD and stop it working. So if you have an RCD that's feeding a number of final circuits, and one of these final circuits is leaking DC back onto the RCD, you can have a situation where it won't actually work when it's called upon to work. So we could have a fault, it could be a serious fault, and the RCD may not work. So that's how serious it is to choose the correct RCD. Another thing you need to consider is how you connect them. If you're putting them in series, you've got to get the hierarchy of how they work. You cannot feed a type B RCD from a type AC RCD because of the characteristics you've selected the type B device for. The presence of DC would also affect the RCD that you're feeding it from. So it's quite hard to explain that, but hopefully the picture there, you can see that where you've got the type B load, you've got that fed straight from what would be some Henley blocks before you've moved into the consumer unit, because you're not going to want to feed it from a lesser type device. Okay, and then you've got the type AC is on the cooker there, is fed from a type A, so that's okay, and that's quite acceptable. And you'll notice that that type A in the middle there is time delayed, and that's so we can get selectivity, which we're going to be moving on to shortly. So that's a recap of types of RCDs, why there's an issue when there's DC components, how we've got to look at installing them. There's a lot of considerations to be made there. So looking at this consumer unit here, this is a high integrity consumer unit. And let's imagine that the two RCDs feed in all of those circuit breakers are type AC devices. Okay, now the customer wants an electric vehicle charger, and you've looked at your vehicle charger manufacturer's instructions, and it says that you can use a type A device because the charging equipment has got DC monitoring built into it. Okay, so type A is a good selection. Now you can, if there was a spare way on one of those existing sides of the boards, you could not feed it from there because of the issues we've just talked about. So in this case, you're going to use the high integrity side of the board and put it on an RCBO, and that's how you can get compliance with that kind of situation if you're lucky enough to have a high integrity board at the front end. Next up, we're going to be looking at selectivity between RCDs. This is another new regulation, and it gives us some specific requirements. Where selectivity is required between RCDs that are in series, the upstream RCD should be suitably time delayed. Okay, and the ratio of the upstream to downstream residual current rating should be at least 3:1. Okay, so what this is looking at here is that if we have a fault on RCD 21 there, okay, RCD 21 trips and it doesn't take out RCD 1, because if RCD 1 goes out, then we're going to lose power to RCD 22. Okay, so it's getting that selectivity, which we used to refer to as discrimination before the 18th edition. And this is how it quite simply be achieved. We've got our 30 milliamp for our final circuits on RCD 21, and RCD 1 is 100 milliamp, and it's a S-type time delayed. So we've met the requirements there. We've got the time delay and we've got the 3:1. They don't do a 90 milliamp device, so we've gone one better and we've got 100 amp. We've met our minimum of 3:1 for selectivity. Okay, now sometimes you have to make reference to manufacturer's instructions when you get adjustable RCDs, and you've got to decide how to set those time delays and those current settings in there, and this may be needed when the installation is more complex. So looking at the screen there, trying to achieve 3:1, we've got the final circuits on RCD 21 as 30 milliamp, then we've got a time delay on the S-type there, 100 milliamp. We've got our 3:1 ratio. We've set the adjustable settings at 300 milliamps, and let's say with a 0.3 second delay. Where the question mark is where you'd probably need to talk to the manufacturer to say, how do we set this one to ensure that it won't trip and we get that correct discrimination or selectivity, I should say, between the devices. So the manufacturers have charts and they can tell you exactly where you should set the current and the time delays on there. Sometimes out in the field, when you get a generator out at an event, a common sort of thing would be to set the current rate in. So you may have 100 milliamp, you may put a 0.1 of a second delay on it, a 300 milliamp, a 0.3 of a second delay, a 500 milliamp, a 0.5 of a second delay. That's the kind of thing that we do out in the field. But if you're doing a fixed installation like this, you want to use the manufacturer's instructions and make sure that you can comply. Okay, next up is a regulation regarding unwanted tripping, another new regulation to the 18th edition. Okay, and it states that RCD shall be selected and erected to limit the risk of unwanted tripping. We've always done that anyway, but there's some new requirements and considerations discussed. So it talks about subdivision of circuits with individual RCDs. And it also says to avoid unwanted tripping, the accumulation of protective conductor currents and or earth leakage currents downstream of the RCD should not be more than 30% of the rated residual operating current. So looking at the first point, where we're looking at division of circuits using individual RCDs, that's easily met with an RCBO consumer unit. No more needs to be said. We've limited our chances of an unwanted operation because everything is split up across a number of RCDs. When we look at the second requirement regarding the 30% and the accumulation, it's possibly hard to meet because you don't know what's going to be necessarily on those circuits and what equipment's on there and how leaky it is, and you could quite easily build up a 30% of a 30 milliamp RCD gives a maximum allowable amount of 9 milliamps leakage. So just looking at this consumer unit here, if we were to look at, let's say, the RCD closest to the main switch, we've got a 32 amp MCB there for a cooker. The cooker may have some sort of elements that are leaking to earth slightly. There may be a few milliamps there. We've got an immersion heater. We've got some sockets. We don't know what's going to be plugged into those sockets. So as you can see from just a simple setup here with 4 MCBs, we could quite easily approach 9 milliamps. Now those RCDs there, they have to meet a product standard and they mustn't trip, as you know, at anything less than 15 milliamps, and they must trigger before 30 milliamps. So what the manufacturers do is they set them somewhere in the middle, so around about 22 milliamps. And for you guys out there that are doing testing and inspection, you'll know that if you ramp test RCDs and RCBOs, you will get readings on the RCBOs sometimes down to 18 milliamps, and these types of RCDs in consumer units are typically around about 24 milliamps. So they're not always 30 milliamps, they're quite often more sensitive. So it doesn't give much headroom. So what the regulation is basically saying is that, you know, they don't really want you having much more than 9 milliamps on there because you could quite easily reach the trigger point of the RCD. So it's another consideration for you to manage when you're out there choosing the correct type of board. Okay, so moving on swiftly, we've got another new regulation, and this one concerns overload protection of RCCBs. And as I said at the beginning, an RCCB is a RCD in a consumer unit. Okay, now this regulation here, 536432, it gives a statement. It says that RCCBs are intended to protect persons against electric shock. Okay, and it tells us that switches are there to switch loads or circuits. So quite simple stuff. It then says that none of these devices provide protection against overload and therefore shall be protected by an overcurrent protective device. So here's the thing. Let's look at a consumer unit. Okay. That consumer unit, it contains switches, it contains RCCBs. Where's the overload protection for it? So this is a new regulation, and we've got to consider now that the only overload protection for that board is the DNO's service cutout fuse, okay? And we don't always know what that's rated at. So it's quite different when we look at commercial and industrial settings. Almost always we will feed switchgear with a switch fuse or something with a fuse, provide an overload protection. But in a residential situation such as this one, we've got to now look at this regulation and say, how do we meet it? So unless the upstream protection is known to be a 60 amp or a 63 amp fuse or circuit breaker, the existing consumer units that we used to have with 63 amp and 80 amp rated RCCBs won't fully meet the regs, okay? Overload protection shall not be solely based on the use of diversity factors of the downstream circuits. So this is new wording to the regs, and this is the crux of the problem. It says we cannot solely rely on diversity factors. Okay, so it gives us three options really. The service cutout fuse is not always known. It could be 100 amps, so therefore you could specify a consumer unit with 100 amp rated main switch and RCCBs. And this is where you have to pay attention when you're looking at consumer units out there on the shelves. There will be many still out there with 63 amp RCCBs in them. Some of the manufacturers, because of this regulation, have said we're going to move to 100 amp rated switchgear. So that's great, because if you're using one of those boards, it meets this problem. Okay, you could use an RCBO consumer unit, so there's no problem there. You're not going to overload the individual RCBOs because they've got overload protection built in them, overcurrent protection built into them, so no problem. You still have to consider the main switch rating. Obviously, if you stacked a load of RCBOs up with a load of load on it, you could overload the main switch, so you still need to consider the main switch rating. And then finally, you could guarantee that the sum of the rated current of downstream circuit breakers does not exceed the rating of the main switch or the RCCB. So if you had a 63 amp device and you had a load of 6 amp breakers on it and they didn't add up to the 63 amps, that's fine, that's no problem, okay? But be aware that it could be compromised if there's any spare ways on the board, because somebody could come and put an additional load on, let's say a electric vehicle charger. It's got that constant heavy load on it, and it could overload the RCCB now. So that's your three options, okay? So when we talk about these 18th edition consumer units, let's look at this image here. This is what we're talking about. The manufacturers moved to 100 amp rated device there, allowing you to put it straight onto the front end like we've always done, and we don't need to consider what the rating of that service cutout fuse is, because the switch gear can handle the 100 amps, okay? We talked about the types of RCCBs. These manufacturers quite often now are moving to type A devices, okay? So when you're buying or purchasing your boards, considering what we spoke about previously, you could be looking at 100 amp rated switch gear. Also, are the RCBOs able to handle the presence of DC current? So a lot of the manufacturers are moving to type A RCCBs as standard, but not all of them. There'll still be the AC types out there, so be aware of that. And it's quite hard to spot the little symbols on the devices, and a top tip for that really is to take a picture of it, and then you can expand the picture on your phone and you can see it easier that way. We're getting on to the subject of integration of devices and components now. Another new regulation, 5364203. And when you see these regulations, the 200 numbers at the end, they're UK only regulations, okay? So in this case here, we're looking at a consumer unit with products that have been mixed and matched, okay? Now, we've probably all done that over the years to help customers out, and the good engineers out there will look at the lineup. Does it look like it's going to fit the buzz bar correctly? Is it all good? I don't have to damage the enclosure, etc., etc. And they've done a good job of it. Not always the case, but it can be done, but this regulation now puts a bit of an issue on doing this, and we wouldn't recommend that you do that going forward. Let's have a look at what it says. It says that low voltage assemblies to BSEN 61439 series, which are your consumer units and your distribution boards, the incorporated devices and components must be declared suitable to the manufacturer's instructions. Okay, so when a manufacturer puts an assembly together, he puts all the devices in there, and they put all of their thermocouples in there, and they measure all of the temperature, all of the heat watt losses, and they make sure that it's all singing and dancing and it's all working together and nothing's being overloaded or nothing's overheating, and then they can stamp it to this product standard that it is satisfactory and it's all working good. Now the issue with these mixing and matching is the only thing, let's go back to the picture. The only thing that the MCBs have got in common is the fact that they sit on a DIMM rail. That is the only thing they got in common. So they will all be slightly constructed differently, which means you may not get a satisfactory connection onto the buzz bar. Or it might mean that if they let go under a fault condition, where they exhaust their combustive gases, it may go onto an inlet part of another MCB, or it may go onto a part in the consumer unit where it's not meant to go and cause a secondary explosion. So the whole enclosure is designed to take one manufacturer's device that will all vent the same way and will all dissipate heat the same way, etc., etc. So when you mix them, you cannot guarantee that. So the final enclosed arrangement must be verified by the original manufacturer of the enclosure. Okay, so if you decide to use a different brand, you need to get permission from the manufacturer that they're happy with that. Probably won't be the case in most cases. They're probably going to say they're not happy. And if an assembly deviates from the manufacturer's instructions, the person introducing the deviation becomes the original manufacturer with the associated obligations. So it's quite serious. If you put a different device in there, you take on the obligations, and if anything happens with that consumer unit, even if it's nothing to do with your alteration, you're going to be responsible. The manufacturer will not warrant their board because you've made the deviation. So let's be very clear, we do not recommend this moving forward. You're probably going to ask the question at the end when we go to Q&A about coding. So let's go back to the picture and look at the coding. If you're doing an EICR and you find this type of board, you're going to have to look at it on its own merits. And in this case, if we say that all the switches are in the same orientation, there's no signs of thermal damage, the enclosure's not been bent, buckled, twisted, cut or butchered in any way. The only observation there is that there's mixed branding. You're probably going to need to give that a C3. Okay, it's been sat there for many years. It's still safe for continued use. Okay, some people may say I'm going to do an FI to see what the manufacturer says. Chances are Legrand are not going to accept a BG and a YLEX breaker into their unit, so the FI will only stall the process of finding an outcome, and we feel the sensible approach to this would be a C3. However, if you find any problems, or when the cover's off, the buzz bar is not lined up correctly, it's twisted, buckled, any issues whatsoever, it would drop to a C2. Okay, so be aware of that one. An example here of surge protection devices, which is our last topic on the slides here. Okay, and I'm not going to go too deep into surge protection because, as I said earlier, we're going to look to bring these presentations through to you. Quick updates, keep your CPD up together, and surge protection is one of the ones on the list that we will be doing. So the 18th edition looked at installations and it gave us that risk assessment, and we would decide whether we installed them or not. And with domestic installations, so consumer units, there was that caveat there that said about significant value, and we've got a risk declaration form which is on the it's on the members download section, and basically it's a way of going through it with a client and advising why these devices are needed, and if they don't need it, they can record it there on the risk declaration, the SPD risk declaration. So that's in there, and we've given an example of that in the on-site solutions publication that's out there as well. So we've got this board here now. The customer's asked for over voltage protection, or it's been decided that it's needed for whatever reason. We're going to need to add it. Now, taking into view that we've just talked about mixing and matching products, we've got two options here. One is that we use the same brand, and then quite simply we can use the manufacturer's kits to cable it all up, and they've tested that arrangement and they're happy with that. That's great. If you want to use a different brand for whatever reason, it may be that you prefer that brand, it may be that there's other SPDs within the installation and you want to match the brand. That's all important stuff, and we'll be talking about that on a future webinar. Then fit it external. It can be sat there external to it, no problems. Now we will explain when we cover SPDs at a later date that there is a maximum distance of how you run the towels, and it's quite short. So make sure that if you're going to sit it next to or on top of a consumer unit, that you put it right close to it so that you can keep those cables to a minimum. And like I say, we're going to go into that further later on. And just to cover another point there, you'll notice that we've got a metal enclosure on the consumer unit, which is required under regulation, I think it's 421.1201. It requires non-combustible consumer units and similar switchgear, okay? But we've got a plastic box for the SPD, and that's because a surge protection device is a passive device. It's not classed as similar switchgear, so that's quite acceptable in this instance.